Hello everyone, I am Muskan from BSc Chemistry Honours first year. My roll number is 21. Today I am going to read out the chapter Aryl Halides. Aryl halides are aromatic halogen compounds in which the halogen is directly attached to an aromatic ring. They are assigned the general formula ARX, where AR is phenyl, a substituted phenyl, or some other aryl group such as naphthyl. For example, we have chlorobenzene. It may be pointed out that the term aryl halide does not include aromatic halogen compounds containing the halogen in the side chain such as benzyl chloride. The latter type of compounds, often referred as to Aralkyl halides, are in fact only aryl substituted alkyl halides. Aryl halides need separate treatment because they differ widely from alkyl halides, including Aralkyl halides in their method of preparation and properties. Nomenclature. Aryl halides are named by adding appropriate prefix of the halogen and its position if necessary to the name of the parent aromatic compound. Methods of preparation. Aryl halides are generally prepared by following methods. Nuclear halogenation. Aryl chlorides and bromides can be conveniently prepared by the direct chlorination or bromination of aromatic ring. The reaction is generally carried out at low temperature in the absence of sunlight and the presence of Lewis acids such as ferric halides and aluminium halides, which act as catalyst. The catalyst is generally known as halogen carrier. The usual practice is to add to the reaction mixture some iron fillings, which are converted by the halogen into corresponding ferric halide, which act as the Lewis acid. For example, chlorobenzene is obtained when benzene is treated with chlorine in the presence of ferric chloride obtained in situ by reaction between iron and chlorine. Halogenation normally stops at the monosubstitution stage, but if halogen is used in excess, a second halogen gets introduced mainly into ortho and para position with respect to the first. Similarly, toluene may be chlorinated or brominated in the presence of iron at low temperature, the reaction taking place more readily than in case of benzene. Limitation of nuclear halogenation. As a preparative method, nuclear halogenation suffers from the following limitations. First, in many cases, nuclear halogenation yields mixture of isomeric aryl halides, such as ortho and para isomers, which may be easily separated. It is not always possible to prepare aryl halides with specific orientation of substituents. For instance, metabromotoluene cannot be prepared by the direct bromination of toluene because methyl group is ortho-para directing. Aryl iodides cannot be prepared unless the reaction is carried out in the presence of oxidizing agents like nitric acid and mercuric oxide. This is because iodinization iodination is a reversible reaction and oxidizing agents are needed to shift the process in the forward direction. Aryl fluorides are never prepared by this method because the reaction with fluorine is very violent. It may be emphasized, however, that in spite of the above limitations, direct halogenation of aromatic compound is a useful method for the preparation of aryl halide. This is in sharp contrast to the direct halogenation of alkane, which is seldom employed for the preparation of alkyl halides due to the formation of complex mixture of products. If toluene and higher alkyl derivative of benzene are heated with halogen in the presence of sunlight and absence of Lewis acid catalyst, halogenation takes place in the side chain of our alkyl halides. For example, if Cl2 is used in excess, other two hydrogen atoms of the side chain are also substituted. Second, from diazonium salts. The decomposition of diazonium salts under suitable conditions is probably the best method of preparing alkyl halide. Aryl halides. Aryl chlorides and bromides are obtained by treating the diazonium salt solution with cuprous chloride dissolved in HCl or cuprous bromide dissolved in HBr. This reaction is known as Sandmeyer's reaction. It may be seen that in Sandmeyer reaction, it is the halogen from cuprous halide which gets attached to the benzene ring. In place of copper chloride or copper bromide, it is also possible to use copper powder and HCl or hydrogen bromide. The reaction is then known as Gattermann reaction. Iodo compounds are obtained just by warming the diazonium salt with aqueous potassium iodide solution. The diazonium salts used in the above reaction are themselves obtained from aromatic amines by treatment with sodium nitrite and an acid such as HCl at low temperature. Fluoro- Fluoroarenes are prepared by decomposing the corresponding diazonium tetrafluoroborate by the action of heat. The fluoroborate itself is obtained by the diazotization of a suitable primary amine. This reaction is known as Ball-Steeman reaction. It may be recalled that alkyl halides are usually prepared from alcohols by the replacement of hydroxy group by halogen. However, the hydroxy group attached to an aromatic ring cannot be easily displaced by halogen, and therefore aryl halides are also not prepared from phenols. They are most commonly prepared from diazonium salts, which in turn are obtained from aromatic amines. Third, from organothallium compounds. The a recently discovered method for the introduction of halogen into benzene ring is a very specific way involve the use of thallium trifluoroacetate. Arenes undergo electrophilic aromatic substitution with thallium trifluoroacetate in trifluoroacetic acid to form thallium bis trifluoroacetate, which reacts with potassium iodide to form aryl iodides. The most important aspect of aromatic thalation reaction is that they proceed in a highly specific manner with respect to the group already present. This aspect of thalation enables us to prepare aryl halides containing the halogen in a specific position with respect to the group already present as illustrated below. Arenes containing substituent groups such as alkyl and halogens undergo thalation para position. This is because the attacking electrophile is very bulky and the reaction takes place faster at the uncrowded para position. The thalated arenes in turn yields para-substituted aryl halides. At higher temperature, the above reaction leads to the formation of metaproducts. Physical properties of haloarenes are similar to those of corresponding alkyl halides. Physical state: in general, haloarenes are colorless, oily liquids or crystalline solids. Density and solubility: they are heavier than water and insoluble in it, but they are soluble in organic solvent. The para compound being generally less soluble in a given solvent than the orthoisomer. This fact is often made use of in the separation of ortho and para positions. Melting and boiling points: the melting and boiling points of haloarenes are nearly the same as those of an alkyl halide containing the same number of carbon atoms. Amongst themselves, the melting and boiling point increases as the size of halogen atom increases. In other words, for the same aryl group, the melting points and boiling points follow the order: iodo, bromo, chloro, fluoro. For the same halogen, the melting and boiling points increases as the size of aryl group increases. For ortho, meta, and para-isomeric dihalides, the melting point differ very widely, while boiling points show much lesser variation. For instance, the melting point of ortho, meta, and para-dichlorobenzenes are 256, 249, and 325 Kelvin respectively, while their respective boiling points are 453, 446, and 448 Kelvin. The para-isomer has relatively very high melting point. This is because the para-isomer is very symmetrical and fits better in the crystal lattice. Therefore, it requires much more energy to break the crystal lattice. Chemical properties. The chemical behavior of aryl halide is marked by lack of reactivity under ordinary conditions. Unlike alkyl halides, aryl halides undergo nucleophilic substitution only with extreme difficulty except in the presence of suitable substituents. Moreover, the presence of halogen also deactivates the aromatic ring towards electrophilic substitution. Nucleophilic aromatic substitution. It has been stated above that simple aryl halides do not undergo nucleophilic substitution under ordinary conditions. However, they can do so under strong conditions involving use of high temperature, pressure, or very strong nucleophilic reagents, like a replacement of hydroxyl group. Aryl halides undergo nucleophilic substitution by hydroxy ion when heated with aqueous sodium hydroxide above 623 Kelvin and high pressure. Replacement by amino group. When an aryl halide is heated with aqueous ammonia in the presence of cuprous oxide and at high pressure, the halogen atom is replaced by amino group. Similar reaction also takes place when aryl halide is attacked by a very strong base, potassium amide in liquid ammonia. Replacement by cyano group. Alkyl halides react with cuprous cyanide at about 473 Kelvin in the presence of pyridine to undergo replacement of halogen by CN group. Effect of substituents on the reactivity of aryl halides towards nucleophilic substitution. The presence of substituents on the benzene ring has strong influence on the reactivity of aryl halides toward nucleophilic substitution. Effect of electron withdrawing substituent. The presence of electron withdrawing group like NO2, CN, CO2, COOH, SO3H, particularly when present in ortho and or para position with respect to the halogen, activates the aryl halides towards nucleophilic substitution. The para-nitrochlorobenzene form para-nitrophenol when heated with 15% aqueous sodium hydroxide at 423 Kelvin. 2,4-dinitrochlorobenzene changes into 2,4-dinitrophenol by heating with aqueous sodium carbonate at 403 Kelvin, while 2,4,6-trinitrochlorobenzene is converted into picric acid. Merely by warming with water. Effect of electron releasing substituents. In view of activating influence of electron withdrawing groups, it is not surprising to find that electron releasing groups such as NH2, OH, ORR, etc. further deactivate the aryl halide towards nucleophilic substitution. It may be recalled that these groups exert just the opposite influence on electrophilic aromatic substitution, electron releasing groups having an activating influence and electron withdrawing groups having a deactivating influence in that case. However, whether a group acts as activating or deactivating towards nucleophilic or electrophilic aromatic substitution, it exerts its effect mainly at the ortho and para position with respect to it. The reason for the low reactivity of aryl halides toward nucleophilic substitution, the mechanism of these reactions, and the effect of various substituents on the reactivity in nucleophilic substitution are discussed in section 10. Electrophilic aromatic substitution. Aryl halides undergo the typical electrophilic aromatic substitution reactions through the halogens have a deactivating influence on the aromatic ring. It may be recalled that in spite of being deactivator, halogens are ortho-para directors. Other reaction. In addition to the reaction discussed so far, aryl halide also undergo following reactions. Formation of Grignard reagents. Aryl bromides and iodides readily form Grignard reagents in the presence of dry ethyl ether. Aryl chloride do not readily undergo this reaction in the presence of dry ether. However, they do form Grignard reagent if dry tetrahydrofuran is used as a solvent. Woods fitting reaction. When an aryl halide is treated with an alkyl halide and sodium metal in the presence of dry ether, the halogen atom of aryl halide is replaced by aryl group. Fitting reaction. If only aryl halide is treated with sodium in the presence of dry ether, diaryls are formed. Ullmann viral synthesis. When heated with copper powder in a sealed tube, aryl iodides form polynuclear compound. Aryl chlorides and bromide undergo the reaction only if they have electron withdrawing groups like NO2 in ortho or para positions to the halogen. Aryl fluoride do not undergo this reaction at all. Reduction. Aryl halide can be reduced with nickel aluminium alloy in the presence of alkali to form corresponding hydrocarbons. Oxidation. An oxidation of nuclear halogen compound which contain a side chain also halogen atom remains intact while the chain oxidized to carboxyl group. Relative reactivity of aryl halide with respect to alkyl halide. Reason for low reactivity of aryl halides. We have seen above the simple aryl halide exhibit very low reactivity towards nucleophilic substitution reaction. This behavior is in sharp contrast to that of alkyl halides, which are highly reactive compounds. Let us try to see why halogen in aryl halide is rather inert toward nucleophilic substitution. Explanation based upon resonance. An aryl halide is a resonance hybrid of various contributing structures, such as structure 1 to 5 shown below. In case of chlorobenzene, it is evident therefore that the molecule of an aryl halide is resonance stabilized. Moreover, the contribution of structure imparts a partial double bond character to the carbon halogen bond in the resonance hybrid of the aryl halide. In other words, carbon halogen bond in aryl halide is stronger than pure single bond. Thus, in contrast with alkyl halides, aryl halide exists in form of resonance stabilized molecule in which halogen is firmly attached to the carbon. As such, the halogen in aryl halide cannot be easily displaced by nucleophilic reagents. The above interpretation of low reactivity of aryl halide is also supported by their dipole moment values. For instance, chlorobenzene has dipole moment of only 1.7 diopter, while the dipole moment of alkyl chloride are of the order 2 to 2.5 to 2.2. This means that aryl halide are much less polar than alkyl halide. This is obviously due to the fact that the contributing structures such as aryl halide contain halogen carrying a positive charge. Contribution from such structure tend to oppose the development of negative charge on halogen arising from the displacement of electron of carbon halogen bond towards the more electronegative halogen atom. Even though there is still a net displacement of electron toward halogen in aryl halide, it is less than in alkyl halide. This naturally exhibits the displacement of the halogen. Alternative explanation. There is another explanation also for the low reactivity of aryl halide. The carbon attached to the halogen in aryl halide is sp2 hybridized, while that in alkyl halide is sp3 hybridized. Since the effective size of sp2 hybridized carbon is lesser than that of sp3 hybridized carbon, the carbon hydrogen bond in aryl halide is shorter and hence stronger than the carbon halogen bond in alkyl halide. An idea of the bond length of carbon halogen bond in aryl and alkyl halide may be had from the act that carbon-chlorine bond length in chlorobenzene is 1.69 angstrom, while in alkyl chloride the length is 1.80 angstrom. This interpretation is also in line with the less polar character of aryl halide. It may be recalled that an sp2 hybrid carbon atom is more electronegative than the sp3 hybrid carbon atom. As such, the sp2 hybrid carbon of carbon halogen bond in aryl halide is less willing to release the electron to the halogen, and consequently this bond is less polar and more difficult to break. Thus, the low reactivity of aryl halide and that of vinyl halide are already discussed in the last chapter. Towards nucleophilic substitution can be attributed to two reasons: delocalization of electrons by resonance and attachment of halogen to sp2 hybridized carbon. Comparison of reactivity of nuclear and side chain halogen compounds. Reaction of side chain halogen compounds. In order to compare the reactivities of nuclear and side chain halogen derivatives, let us first have a look at the reaction of side chain halogen compound. Side chain halogen derivative resembles alkyl halide in their chemical behavior and are very reactive in nature. They undergo a number of nucleophilic substitution reactions as well as other reactions. Woods fitting reaction. On treatment of side chain derivative with alkyl halide or other aromatic halogen compound in the presence of sodium and dry ether, the halogen atom is displaced by alkyl or aryl group. Friedel-Crafts reaction. Side chain derivative react with aromatic hydrocarbon in presence of anhydrous aluminium chloride to keep higher hydrocarbons. Reduction. Nascent hydrogen from zinc copper couple and alcohol reduces these compounds to yield hydrocarbons. Reaction with magnesium, like nuclear halogen compound side chain derivatives from Grignard reagent on treatment with dry magnesium powder in dry ether. Oxidation. Action of oxidizing agents resulting in the oxidation of the side chain, including halogen atom present in the chain. Mild oxidizing agents like lead nitrate convert the side chain into aldehyde group, while reagents like nitric acid change it into carboxylic acid group. Halogenation of side chain. On treatment with halogen at higher temperature in presence of sunlight and absence of halogen carrier, the side chain gets further halogenated. Reaction of the nucleus. Side chain halogen compound exhibit the usual electrophilic substitution reaction of benzene nuclear as well as explanation of difference in relative reactivities of side chain and nuclear halogen derivative. We have seen above that side chain halogen derivative like alkyl halides or undergo nucleophilic substitution quite readily, while nuclear halogen derivatives are marked by their low reactivity. This may be explained as follows. Nature of carbon-halogen bond. As already explained, the carbon-halogen bond of nuclear halogen derivative in aryl halide acquire a partial double bond character due to resonance. On the other hand, the carbon-halogen bond in side chain halogen derivative is a pure single bond because in these compounds, the carbon carrying the halogen is not involved in resonance. Therefore, carbon-halogen bond in nuclear halogen compound is stronger than in side chain halogen compound. State of hybridization of carbon carrying the halogen. In nuclear halogen derivative, the carbon carrying the halogen is sp2 hybridized, while that in side chain halogen compound is sp3 hybridized. As already explained, the effect size of sp2 hybrid carbon is less than in sp3 hybrid carbon. As such, the carbon halogen bond in nuclear compound is shorter and hence stronger than the carbon halogen bond in side chain derivatives. It is also known that the sp2 hybrid carbon atom is more electronegative than sp3 hybrid carbon atom. This implies that as compared to side chain halogen compounds, in nuclear halogen compound, the electron of carbon-halogen bond are not so easily released towards the halogen. Consequently, this bond is less polar in nuclear relative and is therefore more difficult to break. Mechanism of nucleophilic aromatic substitution by molecular displacement mechanism. Two mechanisms have been proposed: addition elimination mechanism and elimination addition or benzene mechanism. Addition elimination mechanism. First, this is generally accepted mechanism of nucleophilic aromatic substitution. According to this mechanism, the reaction takes place in two steps. Step 1, formation of carboanion. Addition of nucleophiles, the first step in which is the rate determining step, involves the attack of nucleophilic reagent nucleophile on the carbon carrying the halogen to form an intermediate carbon ion, which is a resonance hybrid of various structure. During the formation of this carbon ion, the hybridization of carbon atom concerned changes from sp2 to sp3, and the aromatic character of the benzene ring is destroyed. The carbon ion formed is called Miss-Simmer complex. Step 2, elimination of halide ion. In the second step, halide ion is expelled from the carbanion to yield the product in which aromatic ring has been regenerated. Mechanism affords an example of nucleophilic substitution in which attacking nucleophile reagent becomes bonded to carbon before the halogen leaves. It is important to note that the formation of intermediate carbanion postulate above is not likely to take place under ordinary conditions. From simple aryl halide, it operates only in the case of aryl halide containing electron withdrawing ring substituents like NO2COH, which stabilizes the intermediate carbanion. The above mechanism for nucleophilic aromatic substitution has been recently supported on the basis of element effect, that is, the influence of particular element present in compound on its reactivity. In nucleophilic substitution reaction of aryl halide, the nature of halogen has very little influence on the reactivity of an aryl halide. This means that the reactivity of aryl halide towards nucleophilic substitution is independent of the strength of carbon-halogen bond. This can be possible only if the rate determining step of the reaction does not involve the cleavage of the carbon-halogen bond, as postulated in the step of the reaction does not involve the cleavage of carbon-halogen bond, as postulated in the mechanism given below. Thus, nucleophilic aromatic substitution involves a two-step mechanism in which rate of reaction is determined not by breaking of carbon-halogen bond but by rate of attachment of attacking nucleophile reagent by aromatic ring to form the intermediate carbanion. Thank you.